So now I'd like the opportunity to introduce Gyorgy Pirok. Yeah. Is our Chief Technology Officer at ChemAxon. He's actually been with us for several years. Mensch, how long? 7. Okay. That's and previous to that, he was with Combichem. And what he's going to talk to you about is our reactor product for virtual enumeration. And this was mentioned briefly by Tim in his talk. So Gyorgy's going to go into a broader presentation on that and how it works for virtual reaction enumeration, also product enumeration.
Thank you, Doug. What I would like to talk about is mostly the recent changes in Reactor. If I remember well, Reactor was introduced in about 2003, first review in JAX in 2004. We added a new wizard-like interface during the years, but you couldn't see so much development in the last few years. There were lots of changes behind which were invisible. So now we support multi-core processors, and most of the code has been rewritten. But it will be a change now. So we will introduce some new, more visible developments. And one of these developments is the integration in Instant JChem, which is getting to be our visual platform of chem informatics. And there is a brand new tool. We had a technical training yesterday about Jqm for Excel. So Reactor will appear there as well. And then I will talk about Metabolizer, which is our new software, which is undergoing, and but I can demo it. And Metabolizer is also based on the Reactor technology. I think maybe I will show some slides, but not many. I try to live demo the things, so maybe this was the last one. But you have some slides in the printed manual to remember. So this is what you can see here is the Reactor Wizard-like user interface. Actually, we call the engine Reactor, and unfortunately an application as well, Reactor, but I will try to distinguish the two. So in Reactor, I can open a file which is can contain more than one generic reactions, and we provide one which is reaction library. This file contains 145 reactions at the moment, and one development is in this year that we are creating a new organic reaction library. According to organic chemistry books, so it will contain classic organic synthetic reactions, but we do it systematically by functional groups at the moment. So alkanes, alkanes, halogenated hydrocompounds, amino groups, hydroxy groups. So we will have a much more extensive library soon, and we will release it not in 5.3, but in the next version, and we will extend it continuously. Actually, Reactor, just very quickly I show for those who are not familiar with that you can find the reaction in the library. Certainly you can edit it and add your own reactions as well, but if you want to use ours, you can choose it. You can load molecules from various file formats. I'm just using some built-in examples, some acid halides and some aromatic compounds, and I have to specify an output file. I am overwriting an existing one. We can generate products and reactions sequentially and combinatorially, and we have some advanced options. And if I turn off some of the tricks inside, we will see how a software program enumerates all combinations in 5 reactions and 16 products. And you see that we acylated benzene, indole in every possible regions, which is not good. anthracene in all possible regions. The symmetrical parts are filtered out. Nitrobenzene, which shouldn't react because nitro group deactivates the ring, and bromobenzene in ortho metapara positions. So reactor can work with a SMERX or an RXM file, but it can contain also some additional rules. So in this case, the number of generated compounds are only 5, and if I show you benzene is oscillated, indole is at the 3rd position, naphthalene in the 9th position. If I feed this back, then the next one will be at the 10th position. And bromobenzene in ortho and para position, and no nitrobenzene reaction. So each reaction contains some rules which can influence the specificity of the selectivities, like regiospecificity, stereospecificity, and we can exclude compounds which could cause side reactions or have functional groups which are sensitive for the current reaction conditions. So that was reactor, and some of you probably used it, and this is what we had until now. Let's see Instant JChem 3, which will be released very soon. Okay, so I had to compile it here. And in this Instant JChem, I have some demo tables, and I just loaded the reagent table, which contain, I think, old-range downloadable reagents, plenty of some 22,000, no, 8,000 compounds. So in this case, Reactor Wizard could use files as input. And we didn't develop database capabilities into that wizard because we knew that Instant JChem provides us a nice framework for accessing databases and then managing further the generated compounds, the products. So, and Instant JChem provides a modular framework as well, so we can add new modules, and one of the first modules is a reactor. I generate a new reactor file, say my reaction, and you will see it's on the left in this project manager. Here is our reaction, and this is a single screen wizard anyway. I like these numberings on the left, which leads you through the process. Our intention was to make it as simple and easy to use as possible, to enable the chemists who are most interested in reactions to use this software tool. So the first is that I can draw a reaction or select a reaction from the ChemAxon reaction library, which is loaded. Certainly, I can save my own reactions in my personal library, a user library. So, say I select a reaction from the ChemAxon library. It's loaded here. I can see those rules, what I mentioned, but these are for experts. So if you want, you can use these features, but it's not necessary. So we have one reactant in this reaction schema, so we need to specify a reactant list. One point is that I can specify an entire table which contains my reagents, though I can also specify a list which is a selection of compounds. So if you run a query in Instant JChem, you save the hits in a list, and you can use these selected molecules as an input for reactor. But now I just select the entire reagent table. Reactor is smart enough to find out which reagents can be used. No combinatorial mode is enabled at the moment because we have only one reactant, and the output can go to a new table, for example, my reaction results, and I will generate the products, not the reactions, as I showed in case of the reactor GUI. I can save this and execute. And on the bottom you can see the progress. All of the reactants are tried, but some of them are not feasible for this reaction. And a new table is generated here. And in the meantime, while it's working, you can see the generated products and the standard mole weight and formula fields, which are always calculated. Certainly, you can then continue with these products for the next reactions, using them as reactants, and then you can have even a multi-step combinatorial synthesis. Okay. Do you have any questions about the reactor integration in Instant JChem? Yes?
What about integrating it with experimental data?
Please.
What about integrating with experimental data? I mean, are you making any attempt to take known reaction data and load it into the database and build off known data?
Actually, what we thought about sometimes is to generate the reactions, the generic reactions, on the basis of experimental data, using large reaction databases to construct the rules, which are the most difficult part of creating a reaction according to this experimental data. We consider this a kind of research which is at the borderline of ChemAxon's focus. So we are open to collaborate it with a company or an academic institute, but it can be done or cannot, I'm not sure, but it would be very useful, I think, if you thought about this kind of thing. All right. Yes?
Are there other questions?
There. Over there.
So chemical reactivity often is actually hierarchical, right? It's you take amine, for example, you have primary amine, secondary amine, aniline. If
yes.
it's present in a certain compound, hopefully there's a way to differentiate them of their reactivity.
Yes, actually, the reactor is we are software developers. So though we had some chemistry in the past, we don't consider ourselves to be able to tell how reactions work. We wanted to create a software in which you can set everything. So it is possible to specify a reaction with primary amines or secondary amines or make distinctions in the rules how they behave. Actually, but these reactions in our library are classified by mechanism. So if the mechanisms of the primary and secondary amines are different, in case of some reactions, they give in the same conditions completely different results, they should be two separate reactions.
So, second question: how easy it is to create that rule from not a computer expert but a regular
yes.
chemist?
Actually, the rule language, which is here in this reaction, is at the current form. It's not easy. Smarts are not easy. I was a chemist once, and in my company, I have to tell you, everyone thinks that chemists know smiles. No, I didn't know, and if I talk to a chemist, they don't know, and everyone is surprised why. So chemists just understand the graphs, the structures. So even these smart parts are difficult to handle, not mentioning the syntax. Though we are building a new chemical terms engine, and it will be even more simplified, so it will be more flexible to accept no parentheses is needed, no double equalities, and so we try to make it simpler, but you need some training. But that's a technical thing. The other thing is whether it's easy to create a reaction rule or not. Sometimes easy. For example, Markovnikov rule It's in the chemistry books where there are more hydrogens or the partial charges are different. These are straightforward. But sometimes I have no clue why these are the main products, and I have to play with the lots of parameters to find out what should influence. For example, in the case of the Friedel-Crafts reaction, how to differentiate the activated and deactivated compounds. That it took a while to find out something, which might be not chemically correct exactly, but it separates well the activated and deactivated compounds. Though if you don't like, you can change the rules.
Thank you.
Thank you.
Was there another question over here? Okay.
Thank you. I will show you quickly the Instant JChem integration. Now the Jqm for Excel integration. Jqm for Excel doesn't require Java. It's the .NET based tool, so you don't have to install it on your computer. And we have here a new flag, a new tab, and we will have a presentation about that. I will just want to show you how Reactor is integrated. The nice thing is that in this case, Reactor is integrated in an Excel style. So I have a reaction in a cell here. I have some reagents there. And I can say that here and among the functions, we have Jqm for Excel functions, quite a lot. And I select GC React product structure. We generate the product. Reaction is in this cell. I have to add $, as it is usually required by Excel, to have this cell fixed. And reactant 1 is here. Reactant 2 is here. Okay. And we generated the product. This is the reaction schema. These are the two reactants. And if I drag this down, here you can see the generated products for the reactions. So this is a completely different way of using Reactor. Luckily, the new Excel versions accept much more columns and rows than in the past, so it's a medium-size libraries can be quickly and easily created here. And it also provides you property calculations that you can visualize with the Excel charts. So it's another interface to the same technology.
So are the rules still in there?
No, the rules are not in here at the moment. So this is just a generic schema without rules. So that's why I use the...
Sorry, you can add basically the rules to the function itself. So if you check the parameters of the reactor function.
I'm sorry, yes, here.
If you scroll down on the right side, you can basically see the selected.
Wow, that's great. I didn't know that.
We're always learning, even about our own products.
It shouldn't be there yet. It wasn't there yesterday. Okay. Yeah, and it didn't freeze down as well. So you really worked last night. Okay. So in the second part, maybe I start with a slide. It would be better. I will talk about Metabolizer. Metabolizer uses the reactor engine, which is not these applications what I showed you. And we started this Metabolizer project in collaboration with other companies and the university in the scope of a EU grant, the project, which had the hepatotoxicity prediction on the horizon, which seemed very difficult even at the first day. So for the sake of safety, we chose metabolite generation, which is still very difficult, but seemed maybe possible to do some developments which might be useful. The goals were to enumerate all possible metabolites of a given substrate, estimate the metabolic stability of molecules, predict the major metabolites, not just generate some 10,000s of metabolites from a substrate. For me, it seems similar to generating nothing, but to generate a smaller set which can be identified experimentally as well. And as a reactor, it should be able to operate with various libraries like human, xenobiotic, phase 1 library, or phase 2, or mice, or bacterial, or plant. I'm just jumping over. Here is our very raw metabolism model. It's a hill with some barrels, and on the top we have lots of water in the top barrel, and the different metabolic biotransformations produce metabolites and consume some. So what is a major metabolite? A major metabolite, for example, can be in this barrel, which has wide pipes in which the water comes in, but only slow outflow is there, so it accumulates. So the keyword is accumulation. So we consider major metabolites, those metabolites which are produced quickly and consumed slowly. So the accumulation, which is a relative number, is the highest. Here is Metabolizer, which is also, we give the API. It has command line interface, but this is a standard desktop user interface. And the first thing I have to specify is select a biotransformation library. This is a demo library, a small one here. We haven't finished we have a bigger library containing some more than 200 biotransformations. We are validating this. But I set this library manually. For the prediction, it contains only few biotransformations, so it can work with given substrates. But these are actually very similar to chemical reactions. We use the same engine. So we initialize all the reactions. And these reactions compete with each other. So I have to specify then a metabolite, which I can sketch or load from a substrate. I can sketch or load from a file. This is from Wikipedia with some mental effects. And I can generate the entire metabolic library with lots of metabolites, or we have a faster method which just follows those paths in which the majority of the substrate amount flows through. We call it the major routes. Here I can specify a limit, how many generations I generate, and we have some features to calculate properties and stop the metabolism when we reach a property to small molecules, or the log P or log D is small enough. And I press this fast mode, and it's really fast. We just created four generations, and here on the right we see the major metabolite predicted, which we should jump there. It's here, and here you can see the metabolic step, the pathway steps. First hydroxylation in the alpha carbon, but you see there are two positions, but the reaction selected one of them correctly, and then the oxidation to carboxylic acid. And even if this is in the third generation, and we generated the next metabolites, and still, since they are created more slowly, this third generation compound is predicted as a major metabolite. You can certainly display some useful properties like the exact mass of the compound. So if you want to identify metabolites. If you know just the mass spectra, it gives you some ideas what could be the metabolites. And we have lots of plans to extend this technology. But what we are doing now is the validation of the big biotransformation library. And we created a software which can use literature data to train these competing biotransformations. So we know lots of drugs and the major metabolites of drugs, and we can train the library to reproduce these major metabolites the most. It will never be perfect, but we can, I hope we can reach a good match, and this training tool will be part of the software. So if you want to create your own library and train with your own data, it will be possible. Yes?
So I think this is great that you can search by the exact mass, but can you also focus your search on a particular part of the molecule? Because a lot of times when you get a drug metabolism study, you don't identify the exact metabolite. The drug metabolism group will say, you've got an M+16 and we know it's somewhere here on the left side of the molecule.
Uh-huh.
So it would be great if you also had the ability just to sort of draw a box around the part of the molecule and then say, okay, show me everything that could be an M+16.
Yeah, sounds very interesting. Thank you. I want to add here some filtering as well. So here you can display some metabolites to have a search box here in which you can enter some range, maybe a SMARTS or a query structure or a mass, which should be easy to find. So this filtering should be added indeed. So thank you.